In the previous video, we looked at the relationship between an explanatory variable that was defined by two groups and a quantitative response variable. In this video, we're now going to look at a categorical response variable. We're still going to consider an explanatory variable that is categorical with two groups. So the only thing that is being changed here is that we're going to have a categorical response variable. Let me introduce you to the two-group completely randomized design. If you watched the previous video, you may be feeling a little bit of déjà vu. Indeed, this is exactly the same design that I used in that video. And I'm really trying to make a point here that the design doesn't change based upon whether our response variable is quantitative or categorical. We still have a simple random sample of study participants that are randomized to two conditions, say a treatment and control. The explanatory variable is still a categorical variable that indicates study condition with the values control and treatment. These two groups can actually be defined by something other than control and treatment, but this is the most common setting, so these are the terms that I'm using. The response variable is an outcome that is observed after the intervention, and that response variable can be quantitative, as we saw in the previous video, or it can be categorical, as we're going to see in this video. The conditions must be independent of each other, and observations within each condition must be independent of each other. So everything in the setup is exactly the same, except the measurement of our variable is going to put individuals into categories rather than giving them a quantitative score. Let's look at an example of this. A study conducted in Maryland looked at 6,026 ninth grade students who had completed introductory algebra. Of these, 3,239 students had received formal music instrumental or choral instruction during all 3 years of middle school. For those with music instruction, 2,818 passed the Maryland Algebra Data High School Assessment. Of those with no music instruction, 2,091 passed the test. The explanatory variable here is whether or not the individual was in music instruction for all 3 years of middle school. The response variable is categorical, pass or fail, based upon the test results. If we had collected test result data as quantitative scores, then we could do what we did in the previous video. But in this case, the data were collected in terms of pass or fail. Let's take a look at the data. We're only seeing a little small piece of the data here because there's over 6,000 students in this data set. So here we're looking at some of the students who were indeed in music instruction and who passed. If we continue to look down the data set, we would find some no's for music, indicating they were not in music instruction, and for both groups, we would see pass and fail for the results. How are we going to analyze these data? Let's take a look. Analyzing two-group categorical data. The statistic of interest here is the difference in proportions in the two groups, which I've indicated here as P1 minus P2. P, you will recall, represents the proportion in the sample. But here we have two proportions, one for music instruction and one for without music instruction. P1 minus P2 is estimating Pi1 minus Pi2, the population proportions. That is, if all the middle school students were put into one of two conditions, music instruction or no music instruction, what would these proportional differences be? This is a question of inference, and that's what we're going to look at in this particular image. Here's the standard error of the sampling distribution of proportions. Each individual piece of this formula looks like the standard error of the sampling distribution of a single proportion, that is, p times 1 minus p over n. But here we have two groups, so we simply calculate these separately, add them up, and then take the square root to get our standard error of the difference in proportions. Yes, we can have a sampling distribution for the difference in proportions, just like we can for any statistic. What we would do is we would take a random sample. From that sample, we would categorize into the two groups of music instruction and no music instruction, and then we would determine the pass rate for each group in order to get P1 and P2. Do that over and over and again, an infinite number of times, taking an infinite number of random samples. That would get us the sampling distribution. We're obviously not going to do that. We don't even have time to take an infinite number of samples. But theoretically, we know it exists, and now we know that the standard error of the difference of proportions is given by this formula. We also need the critical value. Just like with a single proportion, we use the z critical value, that is, a value of the standard normal. For a 95% confidence interval, this is going to be 1.96. For a 90% confidence interval, it's going to be 1.645. Those two values are well known to students of statistics because 95 and 90% confidence intervals are the most common, and using the standard normal distribution is what we always have to use when dealing with proportions. As always, if we take the critical value and multiply it by the standard error, that gives us our margin of error, μ. By taking our sample statistic, P1 minus P2, adding and subtracting the margin of error, we will end up with a lower and upper bound for the confidence interval for pi1 minus pi2. So let's do this. First, I'm going to read in the data. Then I'm going to get the frequency distribution. Here it is. We were told that there were 6,026 individuals in this study, and so if I add up all these frequencies, that's what I should get, 6,026. Let's look at the proportions. These are conditional proportions, conditioned on whether or not the individual took a music class. Of those that took a music class, 87% passed, and of those who did not take a music class, 75% passed. So there's a 12 percentage point difference between these two groups. It's important that I say a 12 percentage point difference and not 12% difference. Those have two different meanings, and the difference here is a difference of 0.12 or 12 percentage points. Let's create the bar plot. Yellow represents pass, and we see more yellow for the yes music class status group than for the no music class status group. Now we can use prop tests to compare proportions. You may recall that in the past, when we were looking at a single proportion, we gave to prop tests the parameters, the number in one group, and then the total number. We're going to do that again, except that we have two groups. So here's what I have to do. I have to concatenate together the number in each group that passed. So that's 2,818 in the music group and 2,091 in the no music group. And then I have to concatenate together the totals. If I look up at my frequency distribution, the total in the music group is 2,818 plus 421. I could go ahead and total that up and enter it in, or I can just put it like this, put it with a plus sign. and let R take care of the work for me when it is calculating my confidence interval. Similarly, I need to put in for those in the no music condition the total N, which is 2091 plus 696. Let's compare proportions. The proportion passing that we saw earlier, we see again here, 0.87 for the music group, 0.75 for the no music group. There's a difference here of 0.12. That's in the sample. But what is the difference in the population? It's somewhere between 0.10 and 0.14. Notice that I'm looking at this confidence interval and rounding. So those that take music in the population are going to pass the test at a rate between 10 and 14 percentage points higher than those who do not take music. And that's it. We now know how to compare two groups of quantitative data, compare two groups of categorical data, not just for our samples, but we also know how to make inferences about the differences in parameters.